Hello guys, we are now on the third part of our uh, instructional video series for the topic finite projective planes. We are now to prove the dual of axiom P.4. This is now our third theorem for finite projective planes. This statement, theorem P.3, now states that given 2 points, there is at least one line incident with both of them. Okay, so actually the proof is quite short since this is just a direct consequence of axiom P.3. So for our proof, we have here by axiom P.3, given two distinct points, there is exactly one line incident with both of them. Hence, the theorem follows. Okay, that is, if there is exactly one line, then there must be at least one line incident with both of them. Okay, so the theorem is proven. Let us now proceed to theorem P.4, the dual of axiom P.2. Such statement says that there exists at least one point with exactly n plus 1 with n greater than 1 distinct lines incident with it. Okay? The existence of at least one point on which n plus 1 lines pass through it. Now, its dual, axiom P.2, assures the existence of a line with n plus 1 points on it. So, although there is a figure given there, let us construct our own figure. So, axiom P.2 assures the existence of a line. Let's call it L, line L, wherein there are n plus 1 points. Okay, suppose these are the points. So let us call them P sub 1, P sub 2, P sub 3, and so on up to the point P sub n plus 1. Okay, now it is important to note that these points must be distinct. Otherwise, L would contain less than n plus 1 points if two or more of these points are just the one and the same. meaning there would be less than n plus 1 number of points. So each of these points would be different from the rest of the points on L. Now, axiom P.1 says that the system should contain at least 4 points in which 3 are not collinear. Meaning this n plus 1 points cannot be all of the points in the system because all of these are on the same line. They are collinear. The axiom asserts that there should be 3 points which are not on the same line, meaning there should be another point other than these points here, P sub 1 to P sub n plus 1. So there should be another point not on L. Let's call it P. Okay, so we are assured of the existence of a point P not on L, so that axiom P.1 must be satisfied. Now, axiom P.3 asserts that for every pair of points, there is a line. For every 2 distinct points, there should be exactly one line incident with them. Meaning, since P and P sub 1 are different from one another, these two are distinct, there should be a line passing through these 2 points, P and P sub 1. Let us call it L sub 1 in reference to the subscript or label of this point P sub 1. Also, since P sub 1 is different from P sub 2, and P sub 2 and P are again different from one another, there should be a line passing through P and P sub 2. Okay, let's call this L sub 2. In the same manner, there should be a line connecting or passing through P and P sub 3. Call this L sub 3 until the line passing through P and P sub n plus 1. Let us call this line L sub n plus 1. Okay, now, if these lines are different or distinct from one another, then there are n plus 1 lines passing through P. Okay? But if, let's say, 2 of these lines are one and the same, then there would be less than n plus 1 lines. So to show that there are at least n plus 1 lines passing through P, let us show that each of these lines must be distinct from one another. Now, suppose that is not true. Let us assume that 2 of these lines are the same, meaning there is, let's color that green. There is a line passing through P, connecting it to a point on L, which was counted twice. Take note that these lines connect points from L to P, meaning 2 points from L were connected to P through this line. In other words, this green line should contain 2 points on L. So, it would contain a point on L and another point on L. Again, the points on L are distinct, meaning these 2 are not the same. These 2 are different points on L. But this green line connects these 2 points to P, meaning this green line, should have passed through both points. Meaning, it could have looked like this. Okay. So suppose this point was if this point here was P sub I, and this point here is P sub J, so the green line would be L sub I, which is the same, which happens to be the same as L sub J. Okay? But again, take note, the points on L are distinct points. These two are not the same. But axiom P.3 asserts that for every two distinct points, there can only be one line. Note that line L sub I, which is the same as L sub J, and line L contain P sub I and P sub J. But these 2 points are distinct, meaning only one line contains them. Therefore, L sub I, and L sub J are just the same line. Because all of them contain L sub I and L sub J here. But take note that P is on both L sub I and L sub J. And since this is L, meaning P is also on L. So P must be on L. But it was assumed, or it was derived, implied earlier that P, so we see that P is on L, but it was derived earlier that P should not be on L in virtue of axiom P.1. So we have a contradiction. So we cannot assume, therefore, it is wrong to assume that a single line passing through P would have connected 2 points on L to P. Okay, so this cannot happen. Therefore, each of these lines, N sub 1 lines, would be distinct. So we can say, therefore, at this point, we can safely say that at least N plus 1 lines are incident with P. Okay, this point. Now, the theorem asserts an exact number of lines passing through P. It should be N, exactly N plus 1 lines. For now, we have proven that there are at least N plus 1 lines passing through P. So to show that there are exactly N plus 1, we have to show that there should be at most N plus 1 lines. There cannot be more than N plus 1 lines that should contain P. Now, suppose there is another line that contains P. There was another line contained P, this violet line here. Okay, it was named as L sub N plus 2. L sub N plus 2. Okay, so this time there are more than n plus 1 lines. Now, recall that axiom P.4 say that for two distinct lines, there should be exactly one point incident with both of them, meaning two distinct lines must intersect. So in other words, in the finite projective planes, there are no parallel lines. Every pair of lines intersect. There is no pair of lines which do not intersect. Meaning, this line L sub n plus 2 and L must meet somewhere. So it must contain a L sub n plus 2 must contain a point on L. So this line should intersect L somewhere. Okay, let us call that point Q. So that is point Q. Okay, so this line must also intersect L at a point Q. Now, L, take note, L has exactly n plus 1 points, meaning Q must be one of those points. Okay, so it should be one of this P sub 1, P sub 2, up to P sub n plus 1. So, Q therefore, Q must be equal to P sub some subscript, let's say R, where R here is less than or is between 1 and n plus 1. So it is point here on L. But then the line connecting P sub R and P have been accounted for earlier. Meaning only one line can connect P and P sub R or Q. Hence that line L sub n plus 2 should be one of those n plus 1 lines accounted earlier. Meaning, if this here is line L sub R, then L sub R would be the same as that line L sub n plus 2. Hence, there cannot be more than n plus 1 lines that pass through P. So we therefore say that P is incident with exactly n lines. Okay, so that ends the proof for theorem P.4. Okay. Hey, our video is becoming quite too long. It would be hard for me to upload a very large video. So we'll cut this and discuss the proof of this theorem in our next video. That would be part 4 of our discussion. See you then. Bye.